Electricity faces a fundamental problem that comes with pretty much any product that's provided on demand. Our ability to generate large amounts of it doesn't match up that closely with when we need it. Wind and solar are becoming more cost-effective, but they'll always be unreliable and intermittent sources of energy. Retailers use warehouses to store goods between manufacture and sale. Water utilities use tanks and reservoirs. But the storage of electricity for later use, especially on a large scale, is quite a bit more challenging. That's why power grids are mostly real-time systems, with generation ramped up or down to meet fluctuating demands instantaneously. That's not to say, though, that we don't store energy at grid scale, and there's one type of storage that makes up the vast majority of our current capacity. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about pumped storage hydroelectricity. This video is sponsored by NordVPN. Visit nordvpn.com/practicalengineering to get 70% off a 3-year plan. More on that later. Although it's a very convenient form of energy to produce, transmit, and use, electricity has some disadvantages. We've talked a little bit about the variability in demand and generation capacity in previous videos of this series, but I'll summarize again here. The fundamental problem is that we use electricity like this, with peaks in the morning and evening, but we generate electricity differently. Fossil fuel and nuclear plants generally have a single capacity at which they run most efficiently, with occasional need to go offline for maintenance. Solar, of course, follows the amount of sunlight, with some variability due to clouds, and wind follows weather patterns with potential for lots of variability. You may have heard of the duck curve, which is the name given to our electricity demand minus the contribution from solar. You end up with this funky curve representing the need for other sources of electricity. This creates a challenge because not only does solar power start to die away right when we need it most during peak demands in the evening, it also creates a much steeper demand curve, requiring grid operators to spin up other types of generation more quickly. So, solar power is meeting some of our electricity needs, but it's not necessarily eliminating the need for other sources of electricity. And in some cases, it may actually be making the grid less efficient by contributing to instability and requiring the use of peaking plants that are generally heavier polluters. In fact, peaking plants are the go-to solution for load following on the grid. These are smaller, more expensive sources of electricity that only run for a few hours per day to make up the difference between the base power load and the evening peaks. Another interesting solution to this problem is called demand management, which is influencing the demand for electricity to reduce or shift peaks and match generation capacity better. This can be as simple as marketing campaigns encouraging you to set your thermostat a few degrees higher, to sophisticated systems that can tell your electric car when to start charging. But the holy grail in grid-scale power delivery is simply to let the demand and generation curves be what they'll be, storing energy when generation exceeds demand, and using that stored energy during demand peaks. There are a wide variety of fascinating ideas for storing large amounts of energy, from molten salt to pressurizing the air in old mines, but most of our current grid-scale storage relies on gravitational potential. That is, using excess energy to lift something up, and then using that thing to generate electricity as it falls back down, essentially treating the Earth's gravity like a spring. And the vast majority of our current grid-scale storage does this using water in a scheme called pumped storage hydroelectricity. And I built a little mini-scale version of this as a demonstration. In most cases, the way this works is to have two reservoirs nearby but separated by a large difference in elevation. In this case, two buckets separated by a ladder. At night, when electricity prices are low, you can use that cheap power and pumps to fill the upper reservoir. During the day, when energy prices are high, you use the water in the upper reservoir to spin turbines and generate hydropower. It's essentially a giant water battery, and storing energy in this way has a lot of benefits, besides just shaving off the peaks of the demand curve. Hydropower is one of the most responsive ways to generate electricity. So pumped storage allows grid operators to handle fluctuations in demand quickly. Pumped storage is also valuable in an emergency, providing quick access to power when other sources may be out of commission. Finally, these systems can provide a lot of benefit on small, insular power grids, like on islands, where you don't have as much diversification in the generation portfolio. But pump storage has several major challenges as well, and I'll use this demo to illustrate the big ones. First is energy density, which is the term used to describe how much energy can fit into a unit volume. And this is not a pump storage facility's finest feature. Just for some reference, here's the energy density of gasoline, a lithium-ion battery, and the water in a typical pump storage reservoir. I say typical because the total energy storage is both a function of height and volume. The greater the head above the turbines, the more the generating capacity for a given volume of water. I'm using a little aquarium pump to fill up my upper reservoir on top of this ladder. It's pretty easy to see the difference in energy density between a battery and the stored water. The water in this bucket has about the same gravitational potential energy as the battery in your car's key fob. In fact, to reach the same density as a typical lithium-ion battery, you'd have to have the water stored at a height of approximately outside the Earth's atmosphere, which wouldn't be very convenient for an electric vehicle. In fact, this is one of the main disadvantages of pump storage facilities is that they require a very specific type of site where you can locate two pools near each other while also separating them by as much vertical distance as possible. And even then, because of the low energy density, these are often massive reservoirs that are major civil engineering projects as compared to something like a battery that can be manufactured in a factory. The other major challenge with pump storage is getting the energy back out once you've stored it. Efficiency is the ratio of how much energy you put in versus how much you get out. You never get it all. That's the second law of thermodynamics. But you hope you get most of it, otherwise you built a very big, very expensive battery that doesn't work. As I mentioned, my model reservoir is holding about 1/10 of a watt hour, but that's not how much energy it took to get it there. I kept an eye on the power supply while the bucket filled, and it took almost 7/10 of a watt hour of electricity. That means my pump's efficiency was about 15%. So the most energy I can even hope to recover is a lot less than I put in. Some pump storage facilities can use reversible pumps that act as turbines, but in my case I'm using a dedicated unit. I've got a power resistor as a dummy load, and I'm measuring the voltage and current produced by the turbine to estimate the total recovery of energy. And the numbers don't look good. In fact, with a small amount of pressure, my little mini hydro turbine could barely spin at all. My best estimate is that I was able to generate 2 milliwatt hours from the full bucket. That's a whopping 0.3% efficiency. And this is the other reason we're not hooking up tanks of water to our portable electronic devices. At a small scale, this just isn't a feasible way to store power. Little pumps and turbines just aren't very efficient. But things look a lot better at large scale. Even considering all the potential losses of energy from evaporation or leakage of water to friction and turbulence within the machinery, many pump storage facilities achieve efficiencies of 70% or higher. Of course, that means they are net energy consumers since, as we mentioned, you can't recover all the power used to pump the water to the top. But if the cost of energy consumed is lower than the price they can get out of that energy, minus inefficiencies during peak demand, they can still turn a profit. In fact, you might be surprised how many pump storage facilities actually exist. In the US, the Energy Information Administration has a nice online map where you can go look around and see if there's one near you that you can go visit. Of course, I only had time to go into the basics of pump storage, and there are a lot of interesting advancements on the horizon, like using abundantly available seawater instead of sometimes limited sources of fresh water. Like demand management, pump storage is just one part of increasing the efficiency and stability of the power grid as we work to implement more renewable and sustainable sources of electricity. I'm on the go a lot, which means I connect to a lot of Wi-Fi networks that I don't control. Unfortunately, that means I'm vulnerable to a lot of common tricks used to steal personal information, like creating a fake network to see who logs on. That's why I use NordVPN. I don't have the time or technical understanding to research every web service and network I use to make sure it's safe. And with NordVPN, I don't have to be an expert in online security to keep myself safe. I just load the app, click connect, and it's done. There's no limit on bandwidth, and it works on all my devices. I don't leave my house unlocked when I'm away, I don't write my passwords on post-it notes, and even though there's probably not someone sniffing packets at my local coffee shop, I don't use their Wi-Fi or any other public network without turning on NordVPN. It's so quick and simple, there's just no reason to take that risk. If your privacy and security online is important to you, they're offering an awesome discount to fans of the channel. Visit nordvpn.com/practicalengineering or click the link in the description below to get 70% off a 3-year plan. Use promo code PRACTICALENGINEERING to get an extra month for free. Thank you for watching, and let me know what you think.